Right, so welcome back everybody. This is now week 14 of class. We're really getting close to the end here. So let's just try to make a strong push as we get to the finish line. A few things to announce, of course. As usual, we have a new homework assignment. That's going to be homework 14. It's up there on the board, and part of it is to do this worksheet. Also, there's a quiz coming up, and that quiz is going to be on Thursday. So right when you get to lecture at the beginning of class, I'll give you the quiz. As usual, it'll be about 15 minutes long. And the topic is going to be gravity and circular orbits. Okay, so you've done a lot of problems involving circular orbits up to this point. It should be pretty familiar. So that's what the topic of the quiz will be. Any questions on that? Okay. So we finished the chapter on gravity last time we met. So now it's time to move on to something new, which is momentum. Okay. So this is the last chapter of the textbook that we're going to cover. After we get through this chapter, it's going to be nothing but review for the final. Okay. So this is the last bit of new information you need to absorb. We'll be on this for the next 2 weeks. Okay. So this is all coming from chapter 9 of our textbook. Remember, we're going a little bit out of sequence here, but that's where we're at. All right, so let's get started just by defining momentum. What is this thing? So let's start by trying to define it in words and get an intuitive sense of what it is, and then we'll see what the equation for momentum is. So momentum basically is a measure of how difficult it would be to bring an object to a stop. Okay, so if an object has a lot of momentum, it's very difficult to stop. If it has little momentum, it's quite easy to stop that object. And we know that intuitively, right? But the actual formula for it is given here. The momentum of an object is defined as its mass multiplied by its velocity. So P, lowercase p, is what we use for momentum. That's the variable. And it is a vector quantity, so we put a little arrow on top of the p, just like we do for any other vector. So p is equal to mass times velocity. Of course, velocity is a vector, and mass is just a scalar, so momentum is just in the direction of an object's velocity. Okay, so if I'm moving east, then my momentum is also east. That's the idea. If we think about the units that would have to come along with momentum, you can look at the equation to figure that out. So m, that's a mass measured in kilograms. V, that's a velocity measured in meters per second. So it must be that the SI units of momentum are kilograms times meters per second. Okay, so that's if you just have one moving object. That's how you define its momentum. In a lot of cases, we'll have multiple moving objects all at once. And in that situation, we want to find the total momentum of that group of objects. So it's pretty simple. You just add up the momenta of the individual objects in your system, okay? So if I want the total momentum of all these different objects, I would take P1 plus P2 plus P3, and so on, until I've included everything. So that would be M1 times V1 plus M2 times V2 plus M3 times V3, just applying the definition of momentum. But remember, when we're adding these momentum vectors together, it's not like adding numbers, okay? We're adding vectors, and the math behind that is a little bit more complicated than just straight addition of numbers, okay? So that's what we're gonna be dealing with. Okay, so always important to remember that momentum is a vector. It has both a magnitude and a direction to it. Okay, so with that said, that's just the definition. Let's use that definition to make a few calculations, okay? So for both of these, I'm not going to give you any data to plug in. Instead, just make a reasonable guess about what the mass and the velocity of your object would be in each of these two cases. So using the definition that P is equal to M times V, first, estimate the magnitude of your momentum when you are running at full speed, and give that in kilograms meters per second. And then also estimate the magnitude of your car's momentum when you're driving down the highway, okay, in the same units. So just, again, make reasonable estimates here, see what you get, and then we'll compare our answers. All right, so take a few minutes to go through that. And again, you just want rough estimates here, so if you're within the nearest power of 10, that's all we're doing. Okay, so we should all have some kind of answer for the first part. What are we getting for this? Just throw out any calculation you make.
150.
150 for running at full speed. Anyone get something else?
300 kilograms per meter per second.
Okay. Anyone get something else?
192.
192. So we're getting like a couple hundred. That's typical of a person running. Okay, that's the ballpark estimate we're talking about. What about for the car? Anyone do that one yet?
In the 10,000s.
Yeah, in the 10,000 order of magnitude range. Okay, so here, let's go through those together, okay? By the way, for a person running, maybe a good baseline is the fastest person in the world, Usain Bolt. Top speed is around 10 meters per second, okay? So, I don't know, let's cut that in half. I'm probably giving myself too much credit, but let's just say 5, okay? So here, if we're running at full speed, hold on a sec, this pen is out of ink. This one works. Okay, that one works. So again, running at full speed, our estimate for momentum, and we just want the magnitude here. So that would be the mass times the magnitude of our velocity, which is just our speed. Okay, I'm right around 80 kilograms, so that's what I'm plugging right here. And like I said, let's say 5 meters per second as an estimate of the top speed, okay? So that's about 400, right, kilograms, meters per second, okay? So we all got different answers, but you know, a few hundred is typical, right? Okay, so for the car on the highway, it's the same calculation, but a different mass and a different speed would be relevant. So, okay, what should I plug in for the mass of a car? I mean, we kind of understand what the mass of a car is in pounds, maybe a little bit more easily, a few thousand pounds, right? Depends on what kind of car you have, but I think a reasonable estimate might be 1,500 kilograms for a mid-sized car. And what about the speed? How fast are you driving at highway speeds? Yeah, and then in meters per second, that's like 30-ish in that ballpark. So if you multiply this out, you get 45,000. Okay, so about 100 times more than a person running at full speed. It makes sense. It's a lot harder to bring a moving car to a stop than a running person, okay? So those are some estimates just to get you thinking about this new quantity. So now that we have the definition down, it's pretty simple, just m times v. Now we want to understand, why do we care about momentum in the first place? Well, we care about it because it relates to other quantities, in particular force, okay? So we'll discuss now the relationship between momentum and force. And we'll start with this. Newton's second law. We understand what that is. We've worked with it like countless times in the last month. It's the net force equals mass times acceleration. It turns out there is a more general way to write this that's equivalent to F equals ma, but it involves momentum, okay? So actually, Newton himself wrote his equation this way in terms of momentum, as it turns out. So what does this say? This says the net force equals dp dt. This is a derivative on the right-hand side of the equation. It's telling you about the time rate of change of momentum. So it's saying the net force equals the time rate of change of momentum. It's that easy. So let's work with the definition of momentum that we know, which is P equals m times v, plugging it in here, and just seeing where that takes us, okay? We'll just follow the math and see where that takes us. All right, so the net force is the derivative of momentum. So in place of P for momentum, I'm going to put m times v. Just make that substitution. Okay, so for any of you who have taken calculus, okay, what do we do when we have to take the derivative? And the thing we're taking the derivative of is like a product of two terms. Product. Yeah, use the product rule, right? Product rule for products. So the way this works is like this. You first take the derivative of the first term, which is m, we say dm dt, and then you just multiply the second term, which is v, leave it alone. You don't take a derivative, just v by itself. Then you add to that the first term, left alone, times the derivative of the second term, which gives you dv dt. Okay, so that's how you evaluate this using the product rule. But here's the thing. This term right here, which says dm dt, that's saying the derivative of mass. It's talking about how mass may be changing over time. So typically, if you have an object, its mass is not changing over time, right? In other words, dm dt is 0 because mass is typically constant. That's actually not always the case, just as a side note. Can anyone think of a situation where mass might be being lost or gained from an object?
Burning fuel in a rocket.
Burning fuel in a rocket is the classic case, right? So if you're ejecting fuel out the back of a rocket, it's actually losing that mass. So you have to account for that using this equation right here. So in the study of rockets, you use this equation to see how it's going to move. But if you just have something like a block sliding across the table, then mass is constant, and then this first term goes away, okay? Now let's focus our attention on the second term. Does anyone recognize dv dt, what that is?
Acceleration.
That's acceleration, right? The derivative of velocity with respect to time. That's the definition of acceleration. So this can be written, net force equals mass times acceleration. So that's just to illustrate that we can look at Newton's second law in terms of momentum like this, and it's totally equivalent to F equals ma, except it's more general because it allows us to capture situations where mass is changing, okay? So that's the result. And based on that, we can start to talk about the relationship between momentum and force. Because that equation we just talked about basically spells out the relationship, right? If you have a force, that causes momentum to change. Force is equivalent in a lot of ways to some sort of change in momentum that's happening over time. So let's define some new terms. We'll start with impulse. So impulse, the definition of this, is the change in an object's momentum. Okay, so any kind of change in physics is denoted by a delta. So we have delta P. And as always, that means final value minus initial. Delta P is equal to P final minus P initial. It may be helpful to think about situations where momentum is changing really quickly. For example, like if I just drop something onto a table, like this, it had some downward momentum just before it hit the table, but then as soon as it hit the table, it almost immediately came to a stop, right? So the table changed the momentum, right? So there was a delta P going on there. But what does it take? Like what's necessary to deliver an impulse to an object. In other words, what's necessary to change the momentum of an object? Well, you need to exert a force on it, okay? If I want someone's momentum to change, I need to exert a force. And of course, if we exert a greater force, if F is larger, we can get a bigger impulse, right? If I push something harder, I can change its momentum more. But also, the amount of time that I apply the force for matters as well, right? So if I apply a force for a short time, and then I apply that same force for a longer time, applying that same force for a longer time gives me a bigger change in momentum, okay? So that's just all kind of intuitive arguments to get to this result. When you take physics 45, we're gonna like prove this a little bit more rigorously using calculus, but for now, this is the result. Hopefully it makes intuitive sense. Delta P, that's the impulse delivered to your object, that's its change in momentum. That equals the average force that acts on it over whatever time interval we're talking about, times delta T. That's the amount of time that the force acts, okay? So that kind of spells out this idea that we can have more force or have the force act for more time, and either one of those things is going to give us more change in momentum, okay? So there's the relationship between momentum and force. Okay, we haven't exactly proven it, but hopefully you have an intuitive sense of that now. So, let's do a few examples now that we have this. In the first example, we have a 125-gram ball, which is thrown at a wall, and it bounces off in the opposite direction, as you see here. The speed of the ball is 12 meters per second just before hitting the wall, so that's this picture down here. And then when it bounces back, the speed is still 12 meters per second, but it's going the other way, okay? Let's say that the ball is in contact with this wall for 12 milliseconds. So, of course, during a bounce, it's pretty short-lived, the actual period of contact with the wall, so 12 milliseconds. So two things to calculate. The impulse, that's the change in momentum that the ball undergoes, and then the average force. So how much force was involved in this sort of collision or bounce? So let's start with the impulse, the change in momentum. What do we think that's going to be? So the mass doesn't change, right? M is the same before and after hitting the wall. Does the speed change? So maybe we're inclined to think the momentum doesn't change, right? Who thinks the momentum changed? Raise your hand. Who thinks it didn't change because you have the same mass and the same speed? Okay. If you answered the momentum does change, you're correct. So even though the speed doesn't change, you've changed direction, okay? Momentum not changing means the ball just goes through the wall and it goes in the same direction that it was going before, okay? So momentum has changed because it drastically, suddenly reversed its direction. That's the idea. All right, so let's do the impulse. That's going to be delta P, which is P final minus P initial. So let's be clear on what that means. P final, that's the momentum of the ball after it bounced back. And then P initial is the momentum it had coming in, okay? But we can write this using the definition of momentum as mv final minus mv initial. And then what we can do just for simplicity is take the m as a common factor out, m times v final minus v initial, all right? There it is. So what's our mass? The mass is 125 grams. That's 0.125 kilograms. We want to get this in the SI unit of kilograms, so that's how it is. And then we have V final minus V initial. Okay. These are vectors, all right? We're not just subtracting the speed. We're not just saying 12 meters per second minus 12 meters per second. We also have to account for the direction, okay? So, let's go back to the picture real quick. If the positive x direction is going to the right, it's my V initial coming in that has a positive value to it, right? This one is in the positive x direction. It's my V final, which is going in the negative x direction, okay? Again, I have to really account for that to get this right. So, V final, which is right here, as a vector is negative 12 meters per second I hat. I'm subtracting from that V initial, which is positive 12 meters per second I hat. So there's a really big change in momentum. It's not zero, okay? These don't cancel out by any means. Can someone crunch these numbers? Basically what we have is 12 plus 12 times 0.125 with a negative sign out front. So 24 times 0.125.
3?
It's just 3. So 3 kilograms meters per second I hat with a negative sign out front. So that means the change in momentum is going to the left in the negative x direction. Okay? So now we can find the average force. Because we know that delta P is also equal to average force times delta T, which means we can solve for the average force. So that's equal to delta P divided by delta T. The average force during some kind of collision or bounce like this is just how much did the momentum change as a result of that, divided by how long did it take, okay? That's the average force. What's our delta P? That's minus 3 kilograms meters per second. And then I'm going to include the I hat because it is a vector. And then I'm going to divide out delta T. So 12 milliseconds is how long this took. All right, so just to remind you, milli, the prefix, is 1/1000, or 10 to the minus 3. So 12 milliseconds is 12 times 10 to the minus 3 seconds. Now, someone out there, please crunch that for me to get the result. But also, let's look at the units. We have kilograms on top. And then we have meters on top. And then if we combine these two factors of seconds, it's seconds squared. What is this equivalent to? Yeah, it's a Newton, so it's a force. We expect it to work out as newtons, right? And how many newtons are we dealing with?
Negative 250 newtons.
Yeah, so minus 250. Okay, minus 250 newtons along the x-axis. Okay, that's the answer. So going back to the original picture, we can make sense of this. The wall is going to have to exert a force that way to make the ball bounce off it, right? It's coming in like this. It needs to feel a very strong force going the other way in order to bounce back. That's what it is. It's a 250 newtons of force going in the negative x direction. So any questions on that? Let's do another example where the geometry is a little bit more complicated. So in the example we just did, all the motion happened in one dimension along the x-axis. Now let's do one where there's two-dimensional motion going on. It works the same way, but we have to be a little bit more careful about how we're dealing with vectors, okay? So here's what's going on. We have a rubber ball, mass 275 grams. Initially, it's moving horizontally, just like this. So imagine like throwing this ball horizontally so it's going this way. And it's moving at 12 meters per second just before it hits this board. The board is kind of tilted so that when it bounces off, it goes at an angle. So after bouncing off the board, its speed is 10.5 meters per second. It's going a little slower. And it's moving at an angle of 75 degrees off the horizontal. So 75 degrees from the x-axis to here, okay? So this is our V initial, and this is our V final. So same set of questions. What is the impulse? What's the change in momentum here? And then assuming that the time, delta t, is 74.5 milliseconds, what is the average force? Okay? So for each of these questions, we're going to give a magnitude and a direction. Okay? So the magnitude, of course, is just how strong is the force. The direction is, if I were to express the angle of that force off the x-axis, what would that angle be? All right, so we're all clear on the setup? All right, let's do the math. So we'll start with the impulse. And this works just like before. There is a delta P, which is P final minus P initial. And we can write that as MV final minus MV initial. And it's really important when we subtract MV final minus MV initial that we account for the fact that we're dealing with vectors, okay? So let's think back. Whenever we add or subtract vectors, we break each one up into components. And then we can go through with the addition or the subtraction. So the first thing we want to do is express each vector in terms of the components. Okay, so on the first line here, I'm going to write MV final. The mass is 275 grams, so that's 0.275 kilograms. And then V final is the one that's going off at an angle. Remember, it's 10.5 meters per second at an angle of 75 degrees for V final, okay? So how do I write its x component? That's going to be 10.5 meters per second, cosine 75 degrees, I hat. That's the x component. And if I do the same exact thing except with sine, that will be the y component of this vector. So I'll have 10.5 meters per second, sine 75 degrees, and then we have a j hat unit vector coming along for that. That's just MV final in xy form. Okay, that's what that is. MV initial is what I'm subtracting. So I'm going to do minus and then write the next vector on the next line. It's the same mass, 0.275 kilograms. But now that's multiplying V initial. So V initial, if you recall, that was just going straight along the x direction at 12 meters per second. So as a vector, that's going to be, or sorry, not 12, 12.5 meters per second I hat. And there's no y component here. So I'm just going to put 0 j hat to kind of use as a placeholder. All right? So what we want to do is find the result of that vector subtraction, okay? So here's what you punch into your calculator. For the x component of delta P, we're going to have 0.275 times 10.5 times cosine of 75 degrees. And then we're going to subtract minus 0.275 times 12.5. So that's going to give us just the x component, okay? Now if you crunch those numbers, I'll just tell you what you get. You can follow along and verify, but this is minus 2.69, and the units are kilograms meters per second. That's just the x component of our change in momentum, okay? For the y component, here's how we want to do this. I have 0.275 out front, which I multiply by 10.5, and then sine of 75 degrees. And then I just subtract 0, okay? Y'all see that? Okay, so the result of that is a positive value of 2.789 kilograms meters per second in the y direction. So let's be clear. This right here, that's what we might call delta P x. This is delta P y. Okay? Now what we want is the magnitude of delta P. It's just like any other vector. If I have the x and y components, I can find the magnitude by doing square root x component squared plus y component squared, just like this. So I'm not even going to plug in the values because they're right here. Just take this number squared plus that number squared, all under the radical. And what you're going to find is that it comes out to 3.8748 kilograms meters per second, but we'll want to keep just 3 sig figs on that if we're keeping track of our sig figs. So I'd write the answer as 3.87 kilograms meters per second. So that's the size of our change in momentum, okay? That's the magnitude of it. What about the direction? Do you guys remember, how do I get an angle for a vector if I know it's x and y components? I use the tangent function, right? But also, what quadrant are we in here? We're in the second quadrant because I have a negative x value and I have a positive y value. So what is it that we do when we're in the second quadrant and we use the tangent function to calculate an angle? It's add 180, okay? So that just as a reminder, because we're in quadrant 2, there's a correction, we add 180. So the angle we want is the inverse tangent of delta py over delta px plus 180. So that will give me the angle of this vector off the x-axis. All right, so if you work this out, it comes out to 134 degrees. Okay, so the change in momentum is this as the magnitude, this is the direction. Okay, now here we're going to do the average force. Because this change in momentum, of course, is related to the average force. The result that we just came up with is that the average force is equal to delta P over delta T. Again, it's just how much has the momentum changed divided by how long did it take to undergo that change. All right, one thing I want you to notice right away from this equation is that, delta P is a vector, it's a change in momentum, but delta T is just a scalar, it's a time, okay? So that means the average force is in the same exact direction as the change in momentum, okay? So I already know the direction of this, the average force, it's the same thing, okay? So right away I know the average force is directed at 134 degrees from the x-axis, okay? Because we already worked that out. Just if we want the magnitude of the average force, that's going to be the magnitude of our delta P divided by delta T. So we have that magnitude right here, so we're just dividing out the time. So this is 3.8748 kilograms times meters per second. That's the magnitude of the change in momentum. That's what's going on top. What's going on the bottom is the time, which is 74.5 milliseconds. Again, milli, that's 10 to the minus 3 seconds. I already showed you how this works out unit-wise. This works out to newtons, okay? So can someone crunch those numbers and tell me what does it come out to? Yeah, so 52.0, rounded off, newtons. Okay, so to get the ball to bounce this way, it must be that the board that it bounced off of exerted 52 newtons of force, but not only that, it exerted that force in this direction at 134 degrees from the x-axis, okay? So we determined that just based on how it changed the momentum of the ball. All right, so Any questions on this so far? Hopefully it's bringing back some ideas from the vectors unit that we went over. All right, we're going to do a few more of these examples. So for this one, I want you to try it out. Or maybe actually, let's break this one into parts. I'll get you started on it and then you finish it off, okay? So here's what the problem says. We have a 1.5 kilogram ball of clay, which we drop from a height of 1.5 meters. After we drop it, it falls towards the ground, and then it hits the floor, and then just sticks to it. Okay, so it doesn't bounce back up, it just kind of splatters on the floor. Okay? So, let's say that the floor was in contact with the ball for 15 milliseconds before bringing it to a stop. So, this is happening very quickly, but if you imagine sort of watching this in slow motion, from the moment the ball touched the floor for the first time until the moment when it was completely motionless, that was 15 milliseconds. That's what I want you to be thinking about. So, what's the impulse? That's the change in momentum. And what was the average force? That's what we want to get a handle on. All right, so first thing we need to do is calculate how fast would this falling object be moving just before it hits the floor. Because if you think about it, it goes from moving downwards fairly quickly to not moving at all in a pretty short time, in 15 milliseconds. But we want to know exactly how fast it was moving down before the collision with the floor to make our calculation. Does that make sense? So, how could I go about doing that? How could I tell, how fast something is moving downwards if I drop it from a certain height?
Kinematics.
That's a kinematics problem, basically, right? Free fall kinematics. So we're thinking back to that stuff. Let's do that part of the problem, and then I'll leave you to do the other part. So right now, what we're analyzing is the fall towards the ground. We're just considering that part of the motion. So what's going on with the fall towards the ground? Well, we start off at a height, which I'll call y0 of 1.5 meters. At the moment we hit the ground, our final height, which we call y, is equal to what? 0, right? I want to show in my equation that we've fallen 1.5 meters. Okay, that does it. All right, also, what's my initial velocity? The initial moment here being when I drop it. What's the starting velocity? 0, right? Remember, if you drop something, the moment it leaves your hand, it doesn't have any velocity yet. So the initial velocity is 0. And the final velocity, which is just Vy, is what we're interested in. Okay? Does anyone remember the kinematic equation that would be useful here? It's not the first one we derived. It's the one involving squares, right? Remember this? Vy squared equals v naught y squared minus 2g y minus y naught. All right, you've seen that before. So I'm solving for Vy. And for that, I'm going to take the square root of v naught y squared, but that's just 0 squared, because I start off with 0 velocity. And then I have minus 2 times g, that's 9.8 meters per second squared. And then I have y minus y naught, which is 0 minus 1.5 meters, okay? I do have to be a little careful here, because I'm taking the square roots, okay? When you take the square root, you have a positive and a negative root to consider. And in this case, we want to actually choose the negative root because we're moving downwards. Okay, we have a negative velocity. So what is the result of that? basically square root of 2 times 9.8 times 1.5. Yeah, so it's minus 5.42 meters per second. And with 2 sig figs. So here's the next part, which I want you to try out. Consider the collision with the floor. I'm going to draw the situation, okay? We have the floor here. Okay. First, I'm going to show you what is going on just before we hit the floor. So this is like the moment that we make contact with the floor. What we have is a ball of clay moving down with some initial velocity, okay? So the initial velocity is going to be minus 5.42 meters per second j hat. So as far as the collision with the floor is concerned, that's the initial velocity, because that's just at the moment we hit the floor, okay? And then, that's our initial state. Our final state just looks like this. The ball of clay is splattered on the floor, and what is its final velocity? It's just 0, right? It's brought to a stop. All right, so we're using this coordinate system right here. X, y is going up, so that's why I said the initial velocity is in the negative y direction, but then the final velocity is 0, okay? You have that information. You also have that the mass is 1.5 kilograms, and the time interval for this collision is 15 milliseconds. So you should be able to do the rest. You should tell me what's the change in momentum and what's the average force, okay? So take a few minutes to work it out. All right, how about we go through this one? start with the change in momentum. Okay. That's delta P. Okay, that's P final minus P initial. And what's the definition of momentum? Very first equation we saw today.
Mass times velocity.
It's mass times velocity. So that means we have mv final, that's a vector, don't forget, minus mv initial, that's another vector. But v final is just 0, so we can cross that right off. Okay, so just basically 0 minus mv initial. All right, so we have 0 minus the mass, which is 1.5 kilograms, times v initial, which is minus 5.42 meters per second j hat. So these two negatives cancel to give you something positive, and the result is like 8 point something, right? What is it, 8.13? Keeping two sig figs, 8.13 kilograms meters per second j hat. This means it's going up, by the way. The change in momentum is upwards. That should make sense given that we started moving downwards with a downward momentum. And if we're going to basically get rid of all that downward momentum, we need a delta P that's going upwards. Cancel it out. Okay? Make sense? What about the average force? Well, that's how much the momentum changed during the collision with the floor divided by how long it took to undergo that collision. Okay, so this delta T has nothing to do with how long it took to fall to the ground. It's just how long did it take for the ground to bring it to a stop. Okay? So for that, we have delta P, which we just found, as 8.13 kilograms meters per second. And then j hat unit vector comes along for the ride, divided by delta T, which is 15 milliseconds, that's 10 to the minus 3 seconds once again. Can someone tell me what that works out to?
535.
Yeah, so I'm going to round that to 540 with the two sig figs, and then the units are newtons. We've seen that before. J hat. So again, this is going up. I mentioned that before, that your delta P and your average force go in the same direction. It should make sense that the force is upward, right? If something's moving down, we need an upward force to stop it. All right? Any questions on this? All right, let's keep going. Let's next do sort of a follow-up question. So we're still thinking about that previous example, but let's change it a little bit. Suppose that the ball of clay was in contact for 15 milliseconds, just like before, but instead of coming to a stop when it hit the floor, instead, it bounced back up. And it bounced back up with the same exact speed that it came down with. So in other words, it's coming down at 5.4 meters per second, and it bounces back up, going at 5.4 meters per second, same time interval as before. So compared to the previous example, in this example, would we have a greater amount of force, a smaller amount of force than before, or is it just the same exact amount of force as before? What do we think? All right, so
Smaller.
some people say greater, some people say smaller. Let's put it to a vote. Okay, and just give me your initial thought. Okay, just want to see where you're at. Who says this is going to involve a greater force? A smaller force? Okay, a few for smaller. How about the same? It's going to involve a greater force. Okay, so most of you are getting this right. But why is that? I mean, let's think about it. So there's a bigger change in momentum happening if the ball bounces back up. Okay? That's the main thing to see here. Because it has some downward momentum, If it bounces back up with some upward momentum, that involves a very large change in momentum compared to just downward momentum and then coming to a stop. In fact, it involves twice the delta P as before. So to see that that's the case, let's just do a little bit of math. So basically with this modified example, same question as before, with V initial equals minus 5.4 meters per second J hat. That's V initial just before hitting the ground. But now we're imagining that we bounce back up. So V final, after bouncing back up, is positive. So moving the positive y direction after that. 5.4 meters per second J hat. So what's my delta P going to be? It's MV final minus MV initial, just like before, right? But I'm not just setting this one to 0, okay? So instead, I've got my mass, which is 1.5 kilograms, times my V final, which is positive 5.4 meters per second J hat, minus 1.5 kilograms, times my V initial. Again, I have to be careful. V initial is a vector. It's got a negative sign attached to it already. Minus 5.4 meters per second J hat, like this, okay? So hopefully you can just see that, it's twice what we had before, but what does that work out to? Something like 16 kilograms meters per second J hat. So the force, if we bounce back, is doubled, okay? Force is doubled. All right, we all clear on that? All right. So maybe one more like this. All right, so we have two different scenarios, A and B. In both cases, what we have is a 1 kilogram ball being chucked at a wall and then bouncing off of that wall. In each case, we're going to imagine that the ball comes in at 15 meters per second and it bounces back with the same speed, 15 meters per second, okay? Let's also imagine that in both cases, we're in contact with the wall for the same amount of time, let's say 56 milliseconds. Okay, so same speeds, same delta T, but what's different is obviously the angle, right? In this case, you hit the wall pretty close to head on, and in this case, you kind of graze the wall. So you guys tell me, in which case do we have a greater force? You might already just intuitively know what the answer is, but try to use physics equations to justify your answer, okay? So take a few minutes to do that, and we'll go through it together. Okay, actually, time is kind of getting away from me. I really have like 25 minutes left. So let's just put this one to a vote, okay? Who says there's a bigger force involved in situation A? Situation B? Yeah, so I mean, you probably just can use your intuition on this one, right? If you were to have to slam into a wall, I'd rather kind of graze the wall than do it head on like this, right? There's less force involved by kind of just graze it. But again, we want to be able to justify that intuition with physics, so that's where we'll draw a few diagrams to get a sense of this, okay? Okay, so we're not going to calculate anything here. We're just going to draw some diagrams. Remember how we draw vector diagrams? Adding two vectors together involves what's called the tip-to-tail method, right? So in particular, what we're interested in is this delta P, okay? Whichever one has a bigger change in momentum has a bigger force, right? So let's just review. Delta P is P final minus P initial. P final is the momentum after we bounce off the wall. P initial is the momentum just before we hit the wall. So I'm not actually adding two things together there, I'm subtracting. But remember, I can think of this as P final plus negative P initial. That might be useful, right? So in other words, I'm going to show you a diagram where I'm adding tip to tail, these two vectors, P final and negative P initial, okay? And remember how this looks. We've got a wall here, coming in like this, and then we're going out like this. So this is my P initial vector just before I hit the wall. This is my P final. Okay? So I'm going to start by drawing P final. That's my first vector. That's going into the second quadrant, something like this. Okay? And then what I'm going to do is draw not P initial, which is going like this, up and to the right, but the negative of that, right? Remember, if you have the negative of the vector, it just flips it around. So negative P initial would look something like this. Okay? And then so that's P final plus negative P initial. And then the delta P that results would be going like that. Okay? So, let's just label a few angles here. Let's call that theta right there. That's the angle that my P final vector goes off at. And then let's call this angle up here, let's recognize that that's also theta up there. Okay, there's some symmetry between them. So you tell me, like if I make theta smaller, what happens? I kind of flatten out the whole picture, right? And my delta P gets bigger as my theta gets smaller. As my theta gets bigger, my delta P gets smaller, okay? So in other words, if theta is smaller, and for our purposes that means close to head-on collision with the wall, then we get a larger delta P, larger change in momentum, all else being equal, that means a larger force. Okay? So in the homework, you'll be drawing some diagrams like this just to kind of visualize what the change in momentum during a bounce or a collision would look like. Okay? So I think that's all as far as the first topic, which is, again, the relationship between momentum and force. So any questions before we move on to the next thing? Okay, let's keep going. Next part is conservation of momentum. Has anyone heard of this before? If you've taken high school physics, you probably went over conservation of momentum. Has anyone seen this before? All right, a few people. What does it mean to say that something is conserved? Anybody know? Stays the same, yeah? So this is just a statement that momentum stays the same. It's not that simple. There's some conditions that have to hold for that to be the case. But basically the idea when we say conservation of momentum is that momentum is staying the same. So conservation of momentum is something we're going to prove in a second. But it's an example of something called a conservation law. Okay, what's a conservation law? It's just a statement that there's some kind of physical quantity out there in the world that doesn't change. So even though whatever system you're looking at might be undergoing some changes, There's something about that system that still stays the same even as it's, doing something. So for example, here's an example from chemistry. Antoine Lavoisier is a French chemist, and he demonstrated the conservation of mass in chemical reactions. Okay, so I can mix a bunch of chemicals together, have them transform into new chemicals, so there's some changes happening, but what's not changing is the total mass of all of those chemicals. That's remaining the same. So that's an example of a conservation law. There's some other examples that we're going to see in physics. Conservation of momentum is one we're going to get to here. There's also something called conservation of energy. We'll really get to see the full picture of that in physics 45. Okay? But there are a lot of different examples of this kind of thing. So conservation laws are really powerful because usually that's the most concise, straight to the point way to think about a problem. Okay? If you can identify some kind of conserved quantity, that's usually the quickest way to get to the answer. And also, conservation laws are powerful because they tell you what's possible and what's not possible, okay? It's possible for something to happen as long as it obeys all the different conservation laws. If you can think of something that may happen, but it breaks a conservation law, you know that that's not actually possible, okay? So that's kind of the thinking here. All right, so what we're going to work up to is the idea of conservation of momentum. But in order to use this idea, we need to think a little differently than we've been thinking so far. We need to think about systems of particles. Okay, a system of particles is exactly what it sounds like. You're just studying some collection of particles. Not just one, but a whole bunch of them. That's kind of a shift in our thinking, right? Because up until this point, if we think about like the kinematic equations we've been studying since the beginning of class, what do they describe? They describe the motion of one particle moving through space, okay? So instead of just one object, now we're going to consider a whole bunch of them. And when I say particles, I'm talking about the smallest particles that things are made out of, like atoms, okay? So a system of particles can be a whole collection of atoms that is bound together as a single object. For example, a baseball bat, right? That's got a whole bunch of atoms held together. It's a single object, but it's a collection of many, many particles, right? Or we could be talking about an unbound collection of objects, like, for example, a bunch of balls that are moving around on a pool table, okay? They're not all bound together. Each one is moving independently, but together, what they make up is a system of particles, okay? So that's the kind of thing we want to start thinking about, okay? Okay, now related to that, related to this idea of a system of particles, we have internal versus external forces. So whenever we do a problem, and in particular we're talking about conservation of momentum problems that we'll start to see in a bit, we need to define what our system is, okay? We need to say, there's something going on in this problem, but I'm going to define this as my system. I'm just going to focus on these particular objects, okay? So as an example, right? The pool table that we just saw, your system might be all the different balls on the pool table. But, the planet Mercury is not part of your system. It has nothing to do with what's going on in the problem, right? It's not relevant to the motion that you're studying. So you define your system. You say, these are the objects that I'm keeping track of. And once you've done that, on a picture, you can draw what's called a system boundary. So it's like a little line you draw around your system to say, all this stuff is inside my system, all of this stuff is external, it's outside, okay? And there's nothing special about what you choose or how you draw this boundary, but just choose something and then you have to go with it throughout the rest of the problem, okay? All right, so once it's clear what's in our system and what's outside of our system, we can define internal and external forces. Okay, internal forces are happening inside the system. In other words, these are forces that are exerted between two objects in your system. External forces are coming from the outside. So it's pretty straightforward. So as an example, let's say that we have this situation. We have an adult who's pulling these two kids on a board, okay? So the board is connected to a string, and this person is pulling that. But the two kids who are standing on the board are each holding two ends of a string, and they're both pulling on that, okay? That's the idea. So if we define the system like this, just including the two kids, but not including the adult on the outside, this would be an internal force, right? It's exerted by two objects within the same system on each other. That's an internal force along this string. This would be an external force because it's exerted by something that's outside of our system. Okay, so that's the difference. You clear on that? All right, so that's a really important distinction to make because once we've made that distinction and we have this idea of a system of particles, we can get to the law of conservation of momentum, which we'll talk about now. Okay. So the first result here is up here. If I have a system of particles, multiple objects that can be moving around, this is a result that holds true. The net external force, so add up all the outside external forces over here, equals dp dt. This is the time rate of change of the system's total momentum. So we're talking about a system with multiple objects, so this momentum is the sum total of all of those momenta. So what this is really saying, if you think about it, is that it takes an external force to change the momentum of the system, okay? An internal force can't change the momentum of the system, okay? In other words, like, you can't pull yourself up by your bootstraps. You ever heard that expression? Okay? In order for you to move upwards, there needs to be some kind of outside force acting on your body, okay? You can't use an internal force to move your body, okay? So that's one result we're going to show. The next result we're going to show is this. Let's say that the net external force acting on our system is equal to 0. So we add up all the outside forces and we get 0. What does that tell us? Well, this side of the equation being 0 tells us that this side is also 0. In other words, dp dt is equal to 0. You guys know from calculus what it means when you have the derivative of something and it equals 0? That means it's a constant, okay? In other words, it means momentum is conserved. P, momentum, is conserved. It's not changing over time. It's a constant. Again, that's only true if the external forces add to 0, but if that is the case, then we get conservation of momentum. So oftentimes, the way we write this is P initial equals P final. If momentum's not changing, you look at your system in some initial or starting state, and you say, that's P initial. And then you set that equal to the momentum in the final state. It's not changing, so initial and final should be the same. Okay, that's the idea.
So that would also mean the direction of the initial and final momentums would be the same?
Yeah, exactly. They're equivalent in every single way. Same magnitude, same direction. As long as you don't have any external force. That's true. So let's take a look at where that came from. All right, this is going to be a bit of like a proof. So the general picture is we have some kind of system of particles. There we go. Okay, so we have a system of particles. And I'm going to draw the most generic system of particles in the world. So each particle is just a little dot on my picture. and I'll draw this little boundary around it to show that that's my system. Everything inside of that dashed line is my system. Everything that's outside is external to it, okay? So here's what we know. For a single particle, we know that if we add up the net force on that particle, that's going to equal the mass of our particle times the acceleration, but we can also write this, like I showed you at the beginning of class, as mass times the derivative of momentum. So that's applying to each particle individually, right? The net force on that particle equals dp dt. So what we can do with that is write some kind of expression for the total force on all particles. Okay, so this is how that's going to work. We're going to take all the forces acting on particle number 1, we're going to add those together. Take all the forces acting on particle number 2, we're going to add those together, and do the same with number 3. You just keep going until you've included every single particle in your system, right? That will include all of the different forces, right? So what is that going to equal? Well, sorry, up here, this should just say dp dt, not m dp dt. Okay. So for the first one, I'm going to have dp dt for particle 1. For the second, I'm going to have dp dt for particle 2. And then particle 3, and just keep going until you've included everything, right? So now, I'm going to take this pretty complicated looking expression and try to simplify it. See, what I'm doing here is I'm adding up all the different forces acting on all the different particles, whatever they might be. But remember, we can broadly classify forces as internal or external, right? An internal force would be a force between two particles within my system. Okay, and then an external force would be something that's coming from the outside. Okay? So if I add up all my internal forces, and then I add up all my external forces, that will include everything, right? So we're just broadly lumping things into these two categories. Okay, on the other side of the equation, what do we have? We have derivative with respect to time of P1 plus P2 plus P3 and so on, right? Basically, I can pull out the time derivative operation from the sum of all these momentum vectors, okay? So, let's take a look at both sides of this equation a little more carefully. What do I get when I take P1 plus P2 plus P3 for the whole system? What is that? Just adding up all the momentum vectors. That's the total momentum for my system, right? So this is saying take the derivative of the total momentum of your system. That's the right side. Okay. On the left side, we have the sum of external forces. I'm going to make an argument that the sum of the internal forces is going to go to 0. So let me explain why that is. Anyone remember what Newton's third law of motion says? What's the third law about?
Every action has a reaction.
Every action has a reaction, and it's equal and opposite in particular, right? So here, let me just pick two particles out of the system. Let's just say let A and B be any two particles in my system. Okay? What the third law says is that, let's say, particle A is exerting a force on particle B. That force we call FAB. if that is happening, we know there's an equal yet opposite force, FBA, minus FBA, is how we write that, okay? So if one particle in my system is exerting a force on another, that particle is exerting a force right back on the other, and it's equal and opposite, okay? And you see, these are internal forces because they're between two particles in my system. But for every internal force that I have an equal and opposite internal force, right? For every FAB, I have a minus, FAB basically, right? So if I add these together, what do I get? I get 0, right? So if I add up all the internal forces, they come in pairs, which cancel each other out, so that the sum has to be 0. That's why we know the sum of all the internal forces is going to equal 0. So that gives us our result right here. That the sum of external forces equals dp dt for your system, okay? It's the external forces, when added together, that give you the time rate of change of momentum in your system, okay? And what conservation of momentum says is that if you don't have any external force overall, then dp dt for your system is 0. And that just means momentum is staying the same over time. It's not changing. In other words, it's conserved. So that's the law of conservation of momentum right there. When you have no external force, then momentum is conserved. Keep in mind, if you do have an external force, then momentum will not be conserved, okay? So we're going to go into some detail about how to use this on Thursday.